All right, so hello again.
Paano daw yung kimchi?
Wait lang. All right, so sorry for that. Okay, so let us continue now our discussion. So let me just check if you guys are over in front of your computers. Just give me thumbs up. Okay, so there were four who are not here yet, maybe. All right, so anyway, so I hope we are clear with the positive clamper circuit. Okay, so let's now proceed to the negative clamper circuit. So in here, everything is the same. It's just that the polarity of our dye is now, it's now different. So before it's negative to positive, but in here, we now have the positive to negative. So as usual, since this one is called negative clamper, so this one doesn't accept a positive output. So all of our voltage input was shifted into a negative half cycle. So if we have twice dBm or positive twice dBm. We also have twice or negative, twice, but it's now negative of your BM. Okay. So once you fully understood this positive clamper circuit right here, then you can also fully understood this one. It's just a matter of changing the, uh, you know, the call this one signage, okay, from positive into a negative. Okay, but before we proceed to that one, so uh, this sine wave is just one kind of a waveform. So we have a lot of different kinds of waveform. So we can have a square wave. Okay. So of course, if we have an input of square wave, we will also have an output of a square wave also. Okay. So from this kind of input, so it's not negative twice of your uh, BM. Okay, but in the form of a square wave. So we can also have a triangle or a sawtooth. Okay, so all of them have their own advantages and disadvantages. So if you want a peak, middle peak voltage, so maybe you can use this triangle. And then if you want to get the, let's say, the part wherein it will go up and then it will go down, so maybe square wave is a perfect one. But overall, so sine wave is the most common one, since I don't know, because maybe this is how a actual waveform of the electricity uh, you know can be seen on a, let's see, oscilloscope. Okay, but yeah, we can form a square, a triangle, or a sawtooth. Okay, with the use of a, or via configuration, of course. So yeah, those are the different kinds of a waveform that we can use. So let's now continue with the negative clamper. So how does a negative clamper work? So the same with how does a positive clamper work. It's just that in here, it only accepts the negative half cycle. So the same thing, okay, with this one. So I guess Let's have a step-by-step scenario. So same thing, of course, we have to charge, okay, your capacitance first. So we have to make this one a closed circuit or a forward bias. And in order for us to make this one forward bias or a closed circuit, this one should be a positive half cycle. Okay, so positive to positive and then negative to negative. So with that, we will have a closed loop current right here. So for the positive half cycle, so VO is still equal to zero since the current will never flow in this RL right here, and then the VMC is equal to, so this one will be positively charged and then this is negatively discharged. So as you guys can see right here, we now have negative of your VI. Okay, and then during the negative half cycle, so we still have the same formula, which is VO is equal to VI plus VMC. All right. So during the negative half cycle, we now have a value of negative VI plus negative of VMC, since this one is negatively discharged. Okay. So if you are going to add those two, it's now equal to negative twice of VI or negative twice of VM, since VMC is just equal with your VI. Okay. And if you guys are going to compare it right here, so this is what you will get, which is the same with our explanation right here. It's just that we have an ugly writings. So I'll give you maybe 10 seconds to take a look on this one. So in a positive clamper, we've started with negative half cycle, but in here, we have to start in positive half cycle because this is the way that we can charge the capacitor. All right, so were you guys able to get this one so far? Okay, just
Yes.
like what I mentioned a while ago. So positive clamper and then negative clamper, and if it's ideal and then no bias, this is this is already a bonus, since whatever is your input, you already know that it's just twice of the output. Okay. So here is the example of negative clamper. So as you guys can see, we have 8 volts and this is a negative clamper. So our voltage output during the negative half cycle, as usual, it's now twice of your VI, which is now negative 16. Okay, and then the value of your VMC is of course equal with whatever is the value of your VI. Okay, so I'll give you guys 10 to 20 seconds to analyze this one. And then once you're done, or once you're already good with this one, so just give me thumbs up so we can proceed to the next one already. Okay. All right. So very good. So I hope that the others who are not responding, you guys will also get this one or get the idea at least. So again, if ever that you have the questions, just let me know so we can talk about it now. So the sooner the better. All right, so the next one now is a clamper with a biasing voltage. So if we have a positive clamper, we can also have a biasing which is composed of a positive bias or a negative bias. So the same with negative clamper, you can also have a positive biasing or a negative biasing. Okay, so here's the idea. If we have the same sign, positive, positive, right here, positive, positive. So it will just be added to our voltage output, as simple as that. But if we have positive to negative, of course, they have different polarity. So it will be deducted to our voltage output. So the same with this one. So negative to positive is a different polarity. So it will be deducted. Okay, and then negative to negative or negative plus negative is of course, it will be amplified, uh, excuse me, negatively. Okay, so if they have the same sign, it will be added. Different sign, it will be deducted, or it will be reduced. Okay, so let's start with positive, positive. Okay, positive clamper with positive biasing voltage. So as you guys can start here, we have here a positive and then negative signage. So this one is a positive bias. Okay, or we can just also call this one VR or a reference voltage. So reference voltage is equal with biasing voltage. So they are just the same. Okay, so don't get confused with this VR right here. So this is just another terminology or another symbol that they have used, okay, or acronym that they have used with a bias voltage, okay, or VRV. Okay, so in here I will leave the reading part to you guys. So mostly this is talks about the connectivity of your biasing voltage to our diode and then to our voltage input to our diode. So what will happen if we have positive half cycle first, or what will happen if we have negative half cycle first? But the main idea of this one is, as you guys can see, it's still twice of the VM. Okay, it's still twice of the VM. However, we have a small lift of a voltage in here. So as you guys can see, it's not just only twice of your VM anymore. Okay, but there is a lift. Okay, so what is this lift of voltage right here? So that is our reference voltage. So since we have positive, positive, so it will be added to our voltage output. So before it's just the VI and then the VMC, but in here you have to add the VR now. Okay, so this small leaf right here is the value of our VR. And then mostly, okay, mostly VI is always greater than VR. All right, so that is always the case. But yeah, nevertheless, if we have a higher VR than VI, so we can just do whatever you guys are doing. The same with the analysis in Clipper. So it would be better if you will do this one step by step, because with that you will really get the correct answer instead of heavily relying on a given formula. Okay. All right. Anyway, so here is the summary of a passive clamper with positive biasing voltage. So again, we have to make this one a closed circuit first in order for us to be able to charge this capacitor. So we have to have a negative half cycle first. So negative to negative and then positive to positive. So during the negative half cycle, so we have here VR, which is greater than VI. Because again, this VR right here is a DC voltage. So it's a constant voltage, but our VI right here is an AC voltage. So what does it mean? So of course, if it's an AC voltage, so there is a point that it will, start with 0 and then will slowly go up to 1, 2 volts, 3 volts. So it's incrementally, incrementing slowly, and then it will decrement slowly. Unlike in here, we have a constant voltage. So of course, there is a time that VR is greater than VI. So at that time, capacitor is charged by VR itself. Okay, because this one is lower, so it will be dominated by our VR right here. And then as you guys can see, positive to positive, negative to negative. So this will become a forward bias. So there is now a closed current of circuit right here. So as you guys can see, this will flow on our capacitance. Okay, so this will now be positively charged, and then this will be negatively discharged. So if I will draw this one right here, so during VR is greater than VI, so we will have this flow of current. So positive to positive is forward bias. Okay, so we have a flow of current right here. So this will be positively charged and then negatively discharged if we have this kind of flow of current. Okay, so that is during the VR is greater than VI. However, once the VI now is greater than VI, diode now is closed circuit, okay, and capacitor is charged by VI. Okay, so once that happens, VI is greater than VR. Okay, so we have negative, positive, so negative to negative, positive to positives. So we still have forward bias connection. Okay, but this one now will be negatively charged by your VI and then positively charged by your uh, VI also, of course. Okay, so as you guys can see, we have the same polarity. Okay, so this one is negative half cycle, and then once we reach positive half cycle, so this will become an open circuit. Okay, so all of our current now will flow on our voltage. Okay, just wait a second, guys. All right, sorry for that, since my cat is medyo magulo. Okay. Anyway, so going back right here, so during the positive half a cycle, so this will become a reverse bias. So all of our current now will flow to our RL. So the reading of our VO now is equal to VI plus VMC, okay, or we can just simply say that VI again, okay, since this one is positively charged by VI a while ago, and also plus VR, since this one is also positively charged. I mean, negatively charged. Ah, Kabaliktaran kasi, it's the opposite. Yeah, it's positively charged a while ago, but the polarity now is clockwise, so we have to consider this one. So as you guys can see, even though it's positively charged by the VR and then negatively discharged at this point, so we have to consider this signage right here. Okay, so as you guys can see, we have the same polarity, so they will just be simply added with each other. Okay, so not deducted. Right, so we have VI plus VI plus VR. So that is where we get this one. And one thing that I wasn't able to mention, okay, so of course, during the negative half cycle, we have a closed loop current right here. So the reading of VO is whatever is the voltage across this path right here. So a rule of a parallel, okay? So whatever is the voltage across this one is not the same with this one right here, okay? So that is why VO is equal to our VR. And during the positive half cycle, so we have VI plus VMC, or this VMC came from a VI plus VR. So again, I'll give you guys 10 to 20 seconds to analyze everything. And then once you're done, just let me know. Okay, very good, Mr. Segun. Okay, very good, Mr. Isagani. All right, so very good, Mr. Samuel, Mr. Agustin. All right, so anyway, to the others who didn't respond, so just let me know if you have a question. Okay, so let's have an actual example with this one. So again, this one is super obvious already. So it's, if you're going to talk about the VMC of this one, so of course, this one will become 10, so it's twice of your VI, plus your VI will be equal to 12 volts. Okay, but then again, let's have a step-by-step solution. So we have a VI which is equal to 5 volts, and then VR which is equal to 2 volts. Okay, and of course we have to start with a circumstance wherein this diode will be a closed circuit or a forward bias, and that is a negative half cycle. So negative to negative and then positive to positive. So in that scenario, we can now have so this is another way in doing it. Okay, so we could just we could just simply assume that VI is always greater than VR because that is always the case, and then there is only one flow of current that will dominate this entire circuit, that is the VI. So we have negative to negative and then positive to positive, so this will become a forward bias, okay, by this VI. And then as you guys can see right here, we have negative 5 volts. So this will be, we can just skip this one for now. Okay, so we have negative 5, and then we have here negative 2 volts. Okay, so as you guys can see, you can just simply combine those two. And then once it reaches this capacitance right here, so this is now negatively charged by our VI plus our VR, and then it will be positively discharged, okay, at this point. So negative 5 plus negative 2 is equal to negative 7, but this one now will become positive 7 if we're going to consider this signage right here. Okay, so with that, we have now a value of VMC is equal to positive 7. And then VO is equal to our VR. So in here, we have positive 2 volts. So the one thing that we need to consider when it comes to VO is this signage right here, the one that is on above. Okay, so VO is equal to 2 volts. So 7 volts and then 2 volts. So this is during the negative half cycle. And then during the positive half cycle, so positive half cycle. So this one now will become a reverse bias since we have positive to negative. Okay, and all of our currents will now flow to our RL. So for the VO right here, we have VI plus the VMC right here. Okay, so in here we have positive 5 volts plus 7. So we have 12 volts for the voltage output during the positive half cycle. And if you guys are going to compare this one with our answer, we have the same result. Okay, so I'll give you guys 10 seconds, 10 to 15 seconds to analyze this one. And just let me know if you're already done. Okay, very good, Mr. Janridge. Very good, Mr. Awas, Ms. Baclauna, Mr. Francis, Mr. Sagun, Mr. Gilbarty, Mr. Ryan. Great. So yeah, that's how we got this 12 volts right here. So basically, it's just twice of your VI plus your VR. Okay, so even though there is no graph or solution like this, you can already see that the answer is something like that. Okay, so super simple. So let's now proceed to a positive negative or positive clumper with negative biasing voltage. So before it was lifted, but this one now is dragged down, okay, or it was brought down, or it was reduced, okay, into something like this. Okay, so the only thing that has changed is this one. We still have a positive clumper, but we now have a negative bias voltage or a negative reference voltage. So again, for the reading part, I'll leave that one to you guys. So it just explains the connectivities and then what will happen during the positive half cycle or the negative half cycle, and so on and so forth. Okay, so here is the summary of a positive clamper with negative biasing voltage. So during the negative half cycle, so of course VMC is now equal to VI minus VR, since we now have an opposing uh, signage. So it's now the other way around. So you have to deduct your reference voltage now. And then for the VO, so we have to consider this signage right here. So this one is negative VR. Okay. And then for the positive half cycle, so the same formula, we have VO is equal to VI plus VMC. Okay, wherein of course VMC is equal to VI minus VR. Okay. So let's have an actual example for you guys to appreciate what's really happening this one. So calculate the V out during the positive and negative half cycle. So in here we have 7 volts as our VI, and then 3 volts as our reference voltage. So the same scenario. Okay, it's still twice of your VI, but you have to deduct this one now. So 7 times 2 is 14 minus 3. So we have 11 volts as our output right here. So 11 volts for this one, and then negative 3 volts for this uh this waveform right here. Okay, so this time I will not explain how did that happen, but I'll leave the analysis part to you guys, since I think it's very straightforward. Once you fully understood how I explained this one a while ago, you can also understand this one. And if you have a question, so just let me know. So once you're already good with this one, so again, just give me a thumbs up. Or if uh, you haven't get this one yet, so just let me know. Okay, so that we can have a step-by-step solution of this one. All right, so I think I need to explain this part, this charging time. I mean the charging time of the capacitance. So if we have this kind of circuit, we have 7 we have 7 volts as our VI, and then 3 volts for our reference voltage. So again, there is a time that VR is greater than VI. So at that time, VMC is being charged by our VR. Okay, so in here we have negative to positive. Okay, so in here I think there is no, yeah, there is no part where in VR is greater than VI, because initially, even though we have VR is greater than VI, uh, it's already a reverse bias. Okay, so with that, your only option to get the final value for VMC is the one that I've explained a while ago. I think we can still reverse it. Yeah, this one right here. Uh, so this one is reverse bias, though this will become a forward bias once our VI is greater than VR. So as you guys can see, we have a negative 5 volts right here, and then we have negative 2 volts. So they are just simply added with each other. So you can also do this one, okay, with our current example right here, which is 7 volts and then 3 volts. So once VI is greater than VR during the negative half cycle, okay, so we have here oops, negative half cycles and negative, positive. So we have here -7. Okay, this one right here, and then it will pass through this one. And then we have here +3. So -7 plus 3 is equal to 4. And then this is now our final value of our VMC. Okay, so this will be negatively charged by our VI, and then will be positively discharged by our VI. So what is the value of our VMC? So that is positive 4 volts. Okay, so that during the positive half cycle, you can again use the VO is equal to VI plus VMC. Okay, so this now will become positive and then negative. So we have +7 plus 4 is equal to 11 volts. Okay, and then the VO right here during the negative half cycle is equal to our negative VR, which is negative 3 volts. Okay, and if we are going to compare this one, we have the same result. So one more time, to those who were able to get this one, please give me thumbs up so that I can just know the counts of students who were able to get this one. There were only 4 or 5 out of 15. 6 out of 15. Okay, anyway, so again, please, if you have a question, so just let me know so that I can help you. Okay, so that I can clear or clarify your confusions or questions. Anyway, so that's it for the passive bumper with negative biasing voltage. Let's now proceed to negative bumper with positive biasing voltage. So we have different uh, signage again. Okay, so we have negative to positive, so it will be deducted. Okay, so this one is positively, a little bit positively clump, and then most of them are negatively clump. All right, so here is the summary of a negative clumper with positive biasing voltage. So it's just the opposite of our positive clumper, of course. So in here we have to start with positive half cycle because that is the time that this diode will become a forward bias. So positive to positive and then negative to negative, and then this capacitor now will be charged. So since we have started with a positive, so this will be positively charged and then negatively charged by the VI. Okay. And then in here, as you guys can see, we have here a connection of positive to negative and then negative to positive. So it won't be able to flow, okay, or this way around, okay, from a VR to capacitance. So the only way that this will flow is from this VR to VI, okay. So that will only happen once this one is forward biased by our VI, okay. So with that, we have to add that VR by following the symbol itself. Okay, or you can just simply see this is negatively charged since if we are going to follow the uh, signage itself, you will get a negative VR. So to avoid that one, you can just simply see that this will flow from VR to capacitance. So it's from here to there. So this will be negatively charged, and then it will be positively discharged by our VR. And as you guys can see, we have different polarities for that one. So that is why we have negative VI plus VR right here. And then during the negative half cycle, so this one now is reverse bias or an open circuit. So capacitor now will be discharged. So as usual, you can just simply use again our, VO is equal to negative VI plus the VMC itself. Okay, or you can use this one, or you can use this one. So to make everything clear right here, let's have an example with the use of this 10 volts voltage input and then 2 volts for the reference voltage. So again, we have to start where this will make the diode a forward bias, and that is during the positive half cycle. So positive to negative. So this is now forward bias. So this will be positively charged and then negatively discharged by our VI. Okay, so the value of our VI is 10 and then VR is 2. 10 and then 2. So we have here a VI which is equal to negative 10. Okay, and then since this one is forward bias, we can just simply say that this will also flow, or it also has a flow of current from here to there. Okay, so this will be negatively charged by our VR and then it will be positively discharged by our VR also. So in here, we now have here a value of the VR itself. So we have VR is equal to positive 2 volts. Okay, so during the negative half cycle, or let's just put the VMC right here first. So we have here VI negative 10 plus 2 is equal to negative 8. And then the VO right here is this VR right here, which is equal to 2 volts. Okay, and then during the negative half cycle, our VO is equal to VMC VI plus VMC, wherein VI is of course negative 10 volts since this one now is negative half cycle. Okay, negative 10 volts plus our VMC is equal to negative 8 volts. So negative 10 plus negative 8 is negative 18 volts. And if we are going to compare this one, we have the same result, of course. Okay, so again, I'll give you guys 10 to 20 seconds to analyze everything. Okay, very good, Mr. Janridge. So in here, uh, it is slightly moved to positive part due to this reference voltage, and then all of them goes to our negative part. All right. So since we don't have enough time anymore, so we will just continue the rest on the part 3. So if ever that you have a question, so please prepare them now so that we can talk about them on the part 3. So goodbye for now, and then again, see you guys later.